Good morning, students. Today we will discuss about Einstein photoelectric equation. Here regarding photoelectric effect, and there are some explanation given by the Einstein, and he given one equation regarding photoelectric effect. That equation given by the Albert Einstein, we are going to call it as Einstein photoelectric equation. And before going to give this equation, and Einstein, before giving this equation, he studied the Max Planck. He is another physicist, famous scientist. He given one theory regarding energy of the light. That theory regarding energy of the light given by the Max Planck. That theory is called as Planck's quantum theory of radiation. In the Planck's quantum theory of radiation, we are going to discuss or we are going to learn the energy regarding the electromagnetic radiation. Means simply regarding the light, we are going to calculate the energy of any given radiation by using one of the equation, that is E is equal to h nu. That equation or that theory is explained by or that theory is given by that Max Planck. And here the Einstein, before going to explaining or giving this equation regarding photoelectric effect, he is going to study or he is taking the consideration of quantum theory of radiation, that is given by Max Planck. And here Einstein, he assumed or he imagined that Max quantum theory of radiation, according to that theory, he considered one sentence, that is the beam of the light, it consists of a discrete sets of energy. That is actually given by Max Planck. Regarding the energy of the radiation, he explained that is the beam of the light, that is consists of a discrete. Discrete means a definite, certain or definite. Getting a definite value of energy. Getting that discrete packet of energy is called as photon, or else called as a quantum. That is actually the sentence given by Max Planck in his quantum theory of radiation. Here Einstein, he considered that one, and he also assumed that is the each and every radiation, or he assumed that the quantum theory of radiation, and what he told, that is the discrete sets of energy, each and every radiation or beam of radiation. Beam of radiation is in the sense more than one radiation, they are coming simultaneously. Getting the bunch of radiations coming, those number of radiations we are going to call it as a beam of radiation. Beam means more than one light. Getting that beam of radiation contains getting a discrete packet of energy. That discrete packet of energy we are going to call it as photon or quantum, not a proton, that is a photon. Here Einstein, he assumed a Planck's constant. He assumed Planck's quantum theory of radiation. Quantum theory of radiation, and he explained that a beam of radiation, beam in the sense that is a number of the radiations, more than two radiations or one radiation, they are moving simultaneously. That sets of radiations we are going to call it as beam of radiations or beam of light. Beam of light consists of discrete packets of energy. Discrete packets of energy called photons. Photon or one more word is there, that is quanta. Quanta or photon, this is same. Not a proton, this is a photon. Photon is a particle, it is not having any mass. That is, the photon is a particle, that is, it is each and every light consists of a smallest tiny particles. Those particles are called as a photon or quanta. Getting, whenever a beam of light, it is consists of a discrete packet of energy. That is looking like this. Getting, this is the radiation and this is a packet of energy. This is a packet of energy. We are going to call it as, this packet contains a discrete energy, a definite energy. This packet of energy is called as photon. This is according to Einstein. Getting, whenever he is before going to explain this one regarding the photon, he used or he assumed whose theory, that is Planck's quantum theory of radiation. And after that, what he is suggesting, let us consider this is the metal, consists of infinity number of electrons. This is the metal, whatever it is the metal, I am not needing it. Whenever this beam of light is incident on the metal, getting, before going to this one, this light is consist of what? Packet of energy. That packet of energy is called as what? Photon or quanta. Whenever this radiation, this beam of radiation or just one radiation you can take, whenever one radiation is incident on the metal surface, its photon energy, means light means it consists of what? Photons, getting a definite energy. This photon of this light, it is transferring its total energy to the electron of the metal. It is a metal, this is a metal. I am using one radiation, consider only one radiation. It is having a certain packet of energy, that is called as a photon. According to Einstein, I am telling, getting this photon in the light, it is transferring its total energy to individual electron of the metal. This radiation transferring or this photon transferring total energy to only one electron, and this light or this photon transfers its total energy to only this electron. And if you consider one more radiation, this radiation or this photon transfers its total energy to this electron. Means here each and every radiation or each and every photon transfers or gives its total energy to individual electron. One radiation is not transferring its total energy, or one photon is not giving it total energy to all the electrons. That's why I am telling, only one photon, it is gives its total energy to only one electron. That's why I am telling, this photon transfers its total energy to individual electron of the metal. Means this light is not giving its total energy to all the electrons simultaneously. That is wrong. That's why he is explaining, one photon gives its total energy to only one electron or individual electron, or in order to give the energy to this electron, then another radiation should be required. In order to give energy to this electron, another radiation should be required. Getting? It means that in order to produce a photoelectric effect, the photoelectric effect in the sense, that is the process of emission of the electron from the surface of the metal. In order to emit the electron from the surface of the metal, this photon or this light radiation, means this photon is transfers its energy to the electrons in two processes. That is when light incident on metal surface, the total metal surface, or you can call it as just matter. Matter is nothing but material. Matter, it transfers its total energy. It transfers its total energy. Total 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 energy, that is photon energy. Photon transfers its energy, total energy, to individual electron. To individual electron means one photon transfers its energy to only one electron, and it is not giving by distribution method. Getting one photon giving its total energy to only one electron of the metal. That's why I am writing energy means to photon energy to individual electron of the metal. Electron of the metal. Getting by utilizing that energy, that electron, by using that energy, it is ejecting from the surface of the metal. Getting here this energy given by the photon to the electron, or this energy given by the photon to the individual electron of the metal, that energy received by the electron, it is utilizing by the two parts. One is whatever it is the energy given by the photon to the electron, that energy is utilized by the electron in two manners. That is, however, the energy given by photon to electron is utilized as that is one, the part of whatever is the energy given by the photon to the electron, that energy is utilized by the electron or used by the electron, that is taking place in two processes. What are those? That is, first one, let us consider this is the metal and this is the electron. Getting here whatever it is, this is I am taking, this is a cathode and this is the anode. This is the anode. This is the light radiation I am using here. Our intention is to emit the electron from surface of this metal. Whatever it is the photon energy, given to the electron of the metal, that energy given by the photon, then that electron uses that total energy of the photon in two processes, in two manners. What is that? Some part of energy. For example, you can imagine the photon have 10 joule of energy. Just you can imagine the photon have 10 joule of energy. Here some part of energy means within 10, for example 3 joule of energy is utilized by the electron for what purpose, and the remaining 7% of energy is utilized by the electron for what purpose. That is important here. Whenever this photon transfers its energy to the electron, some part of this photon energy it is utilized by the electron is just to come out from the surface of the metal. Getting? Just to come out from the surface of the metal, some part of the energy is utilized by the electron, and the remaining part of the energy is utilized by the electron in order to move. Getting? Just here one part of the energy, for what purpose it is going to use? This electron is going to use a part of the energy just to come out from the surface of the metal. After that it is not moving. Why it is not moving? In order to move, it used to have some energy. Getting? Just to come out from the surface of the metal, it wants some energy, and in order to move, or in order to move that electron, in the sense, whenever the electron is moving, then the energy associated with moving particle is called as a kinetic energy. In order to move, it wants some another remaining part of the energy, and in order to just come out from the surface of the metal, it wants some part of the energy. That's why the energy given by the photon is utilized to the electron in two ways. That is, some part of the energy is utilized to the electron just to come out, not for the motion. Just to come out, some energy is utilizing, and to move from cathode to anode. Getting? To move, instead of telling to move, just you can call it as to take the kinetic energy. Getting? Some part of the energy is utilizing as a kinetic energy. Kinetic energy in the sense it is moving. Getting? That's why the energy, the total photon photon energy, the total photon energy is utilizing by an electron in two ways, that is some part of energy, some part of photon energy is used to eject from the surface of the metal, eject from metal surface, and remaining part of the energy just to come out from the surface of the metal, it utilizing some energy of the photon, and remaining energy and remaining photon energy is utilized as kinetic energy of electron. That's why total energy of photon energy is utilized as, this is to eject from the surface of the metal, eject from metal surface, and remaining part of the energy is utilized as kinetic energy of electron. This electron of the each and every electron of the metal utilizes the total photon energy for two ways. That is first one, the electron in order to come out from the surface of the metal, yes, it has to be receive some energy. After ejection, it has to be moved from one point to another point. That's what, in order to move, it has to be receive some energy. In order to move means that is kinetic energy of electron. Getting to eject just from the surface of the metal, after ejecting, it is not moving. In order to move, it has to be receive another part of the energy or some amount of energy. That's why the total photon energy, one photon gives its total energy to only one electron. That one electron uses its total energy for two processes, one for just to eject, another for as I said kinetic energy. In order to move from one point to another point, it has to receive some amount of energy. That energy is called as a kinetic energy. This is the energy utilizing by the electron, or it is the energy given by the photon that can be utilizing by the electron in the two ways, that is just to eject, and that is another part of the energy is utilizing as a kinetic energy. By observing this one means whatever it is the total energy given by the photon that is utilizing by the electron, that by observation of that utilization of the energy by the electron, that Einstein is going to give one equation. Means this electron is emitting from the surface of the metal. First it is emitting, after that it is moving, means it is first emitting, after that it is moving, means kinetic energy. This total phenomena is called as the photoelectric effect. That's why by seeing this observation, he given one famous equation. That famous equation is called as photoelectric equation. Get it? By seeing this one, that photoelectric equation, that photoelectric equation given by the Einstein, that is that one, the equation, the photoelectric equation given by Einstein, that is E is equal to pi naught plus Ke. Ke. This is maximum, means maximum kinetic energy of electron. Total energy of photon. Total photon energy. Photon energy. And this one is work function. Work function of metal. Indicated as phi naught. Work function of metal means it is minimum energy. Minimum energy required by an electron. Required by an electron for what? To just come out from the surface of the metal. To just come out from metal surface. From metal surface. This minimum energy is called as a work function, as you know very well. And this one is after ejection, it has to be moved. Means in order to move, it has to be receive some another part of energy, that is maximum kinetic energy. Maximum kinetic energy of that electron. The kinetic energy of electron plus work function of the metal. Getting minimum energy is required for what? To just come out from the surface of the metal. That is a work function. After ejection, it has to be moved from one point to another point. That is a kinetic energy. That is the energy utilized as a kinetic energy plus the energy utilized as a work function. Together is equal to total energy of photon. And this is the famous photoelectric equation given by the Einstein. That is E equal to pi naught. This is pronouncing it as a pi naught plus maximum kinetic energy. In order to just come out from the surface of the metal, this much is the energy is required. After ejection, it has to be moved. In order to move, this much energy is required. That is kinetic energy and work function. Getting the total energy given by the photon is utilized as work function and kinetic energy. And this is very important equation given by the Einstein. And next one, Einstein equation. Einstein equation in terms of stopping potential. How to write in terms of stopping potential? As you know very well, what do you mean by stopping potential? It is a minimum negative potential given to which plate? Anode plate. For what purpose? In order to stop the moving electron from cathode to anode. Getting? This is stopping potential in the sense it is the negative potential given to which plate? Anode plate. For what purpose? To stop the electron. This is stopping potential. Here, how to write this Einstein photoelectric equation in terms of stopping potential? Let us consider here. We know very well the kinetic energy of electron is equal to 1 by 2 mv square. Getting? This is constant of mass of the electron, velocity of the electron, and this can also be written as E into V naught. What is V naught here? This is E is charge of the electron, that is 1.6 into 10 to the power minus 19 coulomb. And what is V naught? It is a negative stopping potential. Getting? This is a stopping potential, that is this is a cathode and this is a anode. Whatever it is the potential difference between cathode and anode, that is the value of V naught. If the value of 1 by 2 mv square, this value is exactly equal to this value. What is the value of this one? This is the charge of the electron. Getting charge of the electron is this much. And what is V naught? This is the potential difference between cathode and anode. If you multiply this E value and E naught value, that value is exactly equal to 1 by 2 mv square. Here 1 by 2 is constant. Mass of the electron, as you know very well, 9.1. That is 9.1 into 10 to the power minus 31 kg. And this is whatever it is the speed of the electron from cathode to anode. Substitute the value 1 by 2 mass of the electron and speed of the electron from cathode to anode. Substitute and take the value. Imagine if that value is 10 joule, and after that you have to find out that is EV naught, that is the potential difference between those two plates. That's the value into charge of the electron. if you find out this value also, this value exactly equal to this value, that is also 10 joule. That's why the kinetic energy of the electron, it can be written in terms of eV naught also. The magnitude of this term as well as the magnitude of this term is exactly same. That's why the photoelectric equation can be written in terms of stopping potential. How we can written this one? We know that E is equal to pi naught plus kinetic energy, and this can be written as E equal to h into nu. What is h? Planck's constant. Getting this is a Planck's constant. Its value is 6.626 into 10 to the power of minus 31 joule second. And what is nu? This is frequency of radiation. Getting the energy can be given by this equation, and this is exactly equal to h into nu naught. This is Planck's constant, and what is nu naught? This is a threshold frequency. For just rejection of the electron, we need to require a minimum frequency or suitable frequency, that is called as a threshold frequency, plus kinetic energy is 1 by 2 mv square. Getting this can be written as, shift this term this side, that is h nu minus h nu naught is equal to 1 by 2 mv square. Then this one h is common, nu minus nu naught, this is equal to 1 by 2 mv square. This is also Einstein photoelectric equation, but in terms of what? Stopping potential. Getting in terms of stopping potential. Getting this one can be written as in terms of stopping potential, in the sense this 1 by 2 mv square can also be written as h into nu minus nu naught. This is equal to, this can also be written as ev naught. This is ev naught. Getting therefore 1 by 2 mv square is equal to ev naught. ev naught. This is also another form of Einstein photoelectric equation, that is in the form of stopping potential. Getting this is stopping potential, or else you can write this one, or else you can write one more step, that is h by E nu minus nu naught is equal to V naught. This is final one. Yes, this is the final one. Here V naught is stopping potential, h by E into nu minus nu naught. This is another photoelectric, Einstein photoelectric equation in terms of stopping potential. And in terms of wavelength, it can also be written as in terms of wavelength. In terms of wavelength, it can also be written as, that is h by E as it is. Getting nu, I am writing it as c by lambda minus c by lambda naught. This is equal to nu naught. Here how I have written c by lambda instead of nu, because you know very well c is equal to nu into lambda. Speed of light is equal to frequency into its wavelength. That's why here nu is equal to c divided by lambda, just like substituted. Or this is also the Einstein photoelectric equation, but in terms of wavelength. Getting these are three forms of the Einstein photoelectric equations. Whether you can write this one, or whether you can write this one, or whether you can write this one. These three are Einstein photoelectric equation. This is the general Einstein photoelectric equation, and this is also Einstein photoelectric equation, but in terms of stopping potential. And this is also Einstein photoelectric equation, but in terms of wavelength. Getting all three are the different form of the Einstein photoelectric equation, and you can remember this is enough for your exam. Getting this is the concept of Einstein photoelectric equation. Getting next Einstein observations of experimental observations are there. That is Einstein observations of photoelectric effect. That is the next concept that one can be explained in the next class. Getting, thank you.